Greetings everybody, this is Mr. Wakefield once again. We're going to be doing section 3.3 today in our worksheet packet, and this is a big one. This is a big section, a lot of stuff going on here. It's going to take us a little more time than normal to get through it. Lots of good stuff though. It's interesting because even though you see synthetic division and dividing two polynomials here, the biggest thing we're going to be doing in this section is actually learning how to factor a really big polynomial like this right here. Okay, and synthetic division is actually going to help us do that. And it's going to help us do some other things too, we'll see. But you can see here, as we talked about in section 3.2, when you have a remainder of 0, all right, and then you rewrite it as we talked about, where you take the 1 and you change the sign of it, you put it into here, and then you take this bottom line and you put it right here. We talked about all that in 3.2, but we also talked about how you put the remainder here. So if the remainder is 0, what does that mean? That means that I can cross that thing out right there, can't I? Okay, cross that whole thing out, and it's actually just equal to this without the 0, right? That's interesting because when you factor something, what ends up happening? What is the effect that it normally has? And I'm not talking about GCFs here. We'll get into that later. Sometimes you have those as well. But usually when you factor something, at least initially, and I'm going back to the factoring discussion in our prerequisite review packet. That's what this is. Usually a polynomial breaks down to two smaller brackets, doesn't it? All right, and that's what factoring is all about. And sometimes it breaks down to 3 eventually if one of those two initial brackets breaks down further. Well, that's exactly what we're going to be looking at today. All right, we are going to break down to many brackets here in a lot of these problems. Here's what I mean. Since the plus 0 doesn't need to be written, this is just 2 brackets here, isn't it? All right, and that's factoring. If you had a remainder, you guys, like for example, if this had been plus 5 or minus 3 on the end right here, then that's not factoring. You can't have plus or minus a term outside the bracket behind this here and say that it's factored. Factored is when you have 2 or more things being multiplied together, and that's it, not plus or minus something else on the end. That doesn't count with factoring. So that's why this needs to be plus 0 in order to be able to say that, hey, I factored this thing. All right. So the fact that this polynomial right here broke down to 2 smaller brackets being multiplied together with nothing else after that, nothing in front of it either, although sometimes we will have something GCF multiplied by it in front of it, but don't worry about that right now. If you have 2 or more things being multiplied together with no plus or minus outside the bracket at the end here, okay, that is considered factoring right there. And so what this is saying down here is it's saying that if the remainder is equal to 0, then that polynomial right there, x minus k, which in this case would be x minus 1 because the k is equal to 1 up here, that thing is a factor, along with this bigger bracket here, it is a factor of the original function right there. All right, and the reason why is because the plus 0 doesn't need to be written, and therefore you just got your 2 brackets that you would normally get when you factor something. All right. So what's really cool about that is that through synthetic division, we can break down these problems by getting these 0 remainders and getting these brackets. And then what you could do is you can then take the bigger bracket that's still left over, not the one that has the x minus the k number, all right, but the bigger one there with the, where you've got a higher degree than just x to the first. It's, here it's x to the third. That makes this a degree 3 polynomial, all right, because that's the highest degree term. That then could then be factored down further, and eventually you get a whole bunch of brackets a lot of the time, all right. And so that's what we're going to be talking about here. You can break down these bigger polynomials here into a series of brackets, all right. And like I said, there's some additional things you can do with that as well. Let's go ahead and try that here on the first problem. All right. Now, it reminds us up here, let's go through the set. It says factoring a polynomial function that's degree 3 or higher, and all of these are down here at the bottom of the page. All right, we've already learned how to factor, for the most part, when you have a polynomial function that's degree 2 or degree 1, where the highest degree term is 2 or 1. But when it's degree 3 or higher, like these ones down here, or like the one that I just showed you on the front of the sheet, then we got to, most of the time, be a little bit more deliberate about what we do, and this tells us what to do here. Okay. I should make a slight correction here. It says to factor, and we'll talk about finding the zeros, which involves step 6 as well, steps 1 through 6. But it says just to factor these things into linear factors. I'll tell you what I mean by linear in just a moment. But you just need to do steps 2 through 5 right here, not 1 through 5. 1 through 5, the number 1 has to do with when you try to find the zeros. All right, so you don't need to do step 1 there if you're just trying to factor it into linear factors. Now, let me go back to the front side of the worksheet for just a moment, and what we have there. Wanted to talk to you about what linear factors are so that you know what you're looking for. Whenever you have one of these factors that is just, it's a degree 1 polynomial, again, that means that the highest degree term is 1. And again, see how we have x to the first right here? I'm just looking at this low bracket right here. This is x to the first, and then there's no x at all here. So that means this is degree 1 for x to the first, and degree 0 because there's no x at all. All right, so that's a degree 1 polynomial. When you have a factor, all right, and there's 2 factors here because these factors are things that are multiplied together. So these 2 brackets are factors because they're being multiplied together. If you've got a factor, you guys, that is degree 1 polynomial, that's called a linear factor. All right, so we want all of our factors to look like that when we're done factoring each one of these next 3 problems. Let's talk about that and how to make that happen. All right, so let me flip back over. And it helps us out here. It gets us off to a good start here by telling us that this number right here says given that k, which is -5 right here, given that that's a 0. Now remember, we talked about in section 3.2 that if -5 is a 0, then that means that when you plug it into, or when you do the synthetic division, it will give you a remainder of 0. All right? And so let's go ahead and take that -5. Remember, when you have the k number, you don't change the sign of that when you bring it into the synthetic division. But because this is a 0, it is going to, when I put it over here, no sign changing, it is going to give us a remainder of 0, which is going to be what allows us to factor it. All right, and get the 2 brackets there without that remainder on the end. So let me write down the original function here. And you see here that this will come out as 0 here at the very end, like they promised it would. So I bring down the 6. I'm just doing normal synthetic division from section 3.2. Multiply and then add down. Multiply and then add down. Multiply and then add down. And sure enough, it gives you a remainder of 0. What does this mean? This means that we can then use this line right here. Okay. And I'll go ahead and write the original function here. As we learned yesterday, the original function, which was also known. Let me go and pull it up for you so you can kind of remember that. It's easier that way. remember we said that when your function has a k value that's a 0, it makes the remainder 0, but then at the same time, if you take that function, you guys, and you put these two brackets right here, this one coming from the k number where you change the sign and combine it with the x, you then put this bracket here which comes from this line right here of numbers, all right, and then the remainder then would go here, which you don't need to write if it's equal to 0. Okay, so this is exactly what we're going to do here today in this section many times over. So let me say it one more time. All right, when you do the synthetic division on a function where you plug in the k number that you're anticipating will be a 0, anticipating that it will have a remainder of 0, you put the k number there, you do all your synthetic division, and then the k number changes its sign when it goes into here. The bottom line, not including the last number, goes here with its variables, of course, and then the remainder goes here, but if it's equal to 0, you don't have to write it. Okay, so let's do that right here. Okay, the function, when I do the k number and I do the synthetic division right here, it is automatically going to be equal to what? Remember, you got to change the sign as you go from this number out here to the bracket. You got to change the sign, so that would not be x minus 5, it would be x plus 5. Just like we saw yesterday, this number here outside the synthetic division bar and this number that goes inside of this little bracket with the x has to be a different sign. We then multiply that by what? We then multiply that by these numbers here with their variables. What is this variable going to be right here? And the exponent in particular? Well, since this is 6x to the third right above it, this then has to be 6x to the second because it always has to be one exponent smaller. And then we just decrease by one exponent each time. So 6x squared minus 13x to the first, and then plus 2. All right. So now we've done it. We have now broken it down to what? How many brackets are being multiplied together here? It's a total of 2, right? So we have 2 factors now. But here's the problem. Yes, this one is a linear factor, but the other one is what we call a quadratic factor, and it's not linear because remember I said a linear factor is when you have a factor that is a degree 1 polynomial. Okay, in other words, it just has x in it, not x squared or x to the third. Well, this one has x squared in it, and so that is called a quadratic factor when the highest exponent of any of the variables in that factor are or is equal to 2. All right. So again, linear factor if it's a degree 1 polynomial, and a quadratic factor is what it's called if this is a degree 2 polynomial. In other words, the highest degree term is 2 because it's x to the second. All right, so when this happens, remember, we want it to all be linear factors, right? Well, we got one linear factor, so it would be natural then, since we already got one linear factor, we want to leave that one alone. That's what we want it to be, leave it alone. But we want to take this one now and transform this into linear factors. Well, we know how to do that now because we learned that back in, or at least we can try to do it, okay, try to factor down, not everything factors, but we learned back in our prerequisite review packet that when you have something in this form right here, x squared, x to the first power, and then no x at all, with the x squared being positive as well, we learned that we can do what I called back then the Berry method, okay, in order to figure out what terms here are going to go in there to get these two brackets. All right, so let's review that again here. What you do is you take 6 and 2, you multiply that together, and of course that's equal to 12. Oops, I got a little bit ahead of myself there, just a minute. So 6 times 2 is 12. So we want to do 12. And then we want to do what here? We want to do, the middle there is negative 13. Okay. And so I'm actually going to erase this. That's not wrong. It's just I didn't actually show you that way earlier. So I'm just going to do, we got 6 times 2 is 12. We want to keep on listing out pairs of factors for 12 until we get a pair that adds up to negative 13. And as you can see there, 1 and 12 adds up to 13, but negative 1 and negative 12, which also multiplies together and equal 12, so that's okay to use that. That, though, adds up to negative 13, you guys. And so that's going to be what? That's going to be 6x and 6x. Remember, there's a two-step process here to the Berry method where you put the minus 1 and the minus 12 in there, but that's not the final answer there. You got to factor the GCF out of each bracket. The GCF on that first bracket is 1, so it's not going to change this at all. But then the GCF on this bracket is 6. If I factor out 6 out of this, I get x minus 2. And then you throw out that GCF. That doesn't stay when you do it out of the last step of the Berry method. So then I bring that back over here, and I get this right here. And you can see now that all 3 of these things are being multiplied together. And so there's 3 factors total now. Okay, when you have just 3 brackets, later on we'll see when there's a GCF in there as well on the front. But if you got 3 brackets that are being multiplied together and nothing else besides those 3 things, then that's 3 factors. Okay. If you had just 4 brackets, for example, all right, say there was one more bracket after this, all right, then that would be 4 factors if that's all you had were just the 4 brackets being multiplied. So we have 3 factors, but aren't they all linear because they're all degree 1 polynomials? And so we did exactly what they asked us to do. They said to break down this original f of x function into a bunch of linear factors and only linear factors. And so we did just that. All right. And so we're done with that problem. All right. Now, moving on to the next problem here, getting into a little bit more detail here. It mentions here they give us a function again. They give us a k number again, and that they say is a 0 of f of x, which means we can do the synthetic division on it, all that stuff. All right. And that'll get us started here. And then I'll explain the rest of this here coming up. I'll talk about what that word multiplicity means here after that, okay? So we get 2, 1, negative 9. There's no missing terms here, so you don't have to put any zeros in there. Negative 13 and negative 5. And this is guaranteed to give you a remainder of 0. If it doesn't, then I already know there's no misprint on this problem here. I know that this has to be a 0. So you must have done something wrong if you don't get 0 in the end. So please try again and check your work. We'll bring down the 2, multiply, add down, multiply, add down, and you know the process here. I'll keep going, and there we go. We get 0. Very good. All right, now, here's the thing. The original function then is equal to what? The original function then, as a result of the synthetic division, it is equal to, let me just write down the original function here first. Because the remainder was 0, we don't need to write the plus 0 in the end, but we do need to write what here when I factor this. I write down x, and then I need to change the sign of this thing out here, and so it's going to become plus 1. If that had been positive 1 on the outside, then you'd say x minus 1. We talked about that yesterday as well. What's the remaining bracket that's going to go with that? Well, it's going to consist of these coefficients right here. And so that's going to be what? That's going to be 2x to the third. And it's to the third because the number above it was 2x to the fourth. And then you just keep on going down by 1 on your exponent like we've been doing. So minus 1x squared, minus 8x to the first, minus 5. All right, and again, you don't need to write the plus 0. But that leads to what? That means that we now have a linear factor and a bigger factor here that it's not quadratic, because quadratic is when the highest exponent is 2. This is not quadratic yet. All right. But since we got a linear factor, you guys, leave that factor alone. Let it stay that way. Just take what you got over here with the bigger factor, the bigger bracket, and try to now break that down. Okay, it's almost like it's its own separate problem now, where you now need to take this, put that into the synthetic division, and do it again. But you might be wondering, well, how do I know which one, which number to do? Do I do the same number again? Well, you can't always do the same number again. It won't always work. But I want to mention what the multiplicity thing means. It means that the answer will have x plus 1 occurring 3 times. Okay, just like if you have in the last problem we had -5 and x plus 5 appeared in the answer. Because -1 has a multiplicity of 3, instead of x plus 1 appearing once like it did here, like it normally would, the multiplicity 3 means that that factor appears 3 times. Notice please again that this is the factor that is directly linked to -1, because when you go from the k number to the factor, you got to change those signs, right? So these things are all the same, and there's 3 of them because of the multiplicity. They're directly linked to this -1. Okay, so what this means then is, see how we got one of those x plus 1s already? So that means that this leftover part here must have a couple of x plus 1s inside of it. Okay, meaning that if I try to factor this leftover part here, it's going to have an x plus 1 in it. And since it has an x plus 1 in it, that means that since x plus 1 is directly linked to -1, then that means that if I do -1 in the synthetic division, it will give me a remainder of 0 again. Okay, x plus 1 would not be a factor of this like it's supposed to be unless you got a remainder of 0 when you took -1 on the outside. Again, as you go from the factor here, you guys, over to here and vice versa, from here to the factor or from the factor over to here, okay, in both cases, the signs change. So since I know that x plus 1 is a factor of this, I know that if I put -1, let me make some room here for that. If I put -1 into, don't go back to the original function. I'm trying to factor what's left over now. Okay, we've already factored the original function down a little bit to a couple of factors. I want to leave the x plus 1 alone. So I want to take the other part here that I want to break down further, and that's the part I want to break down into more factors. Okay, and because of the fact that -1 has a multiplicity of bigger than 1 right here, we know that -1 is going to work again here. All right, so let's bring down the 2. Multiply by -1, we get -2. Multiply by -1, we get 3. Add, we get -5. Multiply by -1, we get 5. And sure enough, there you go. We get a remainder of 0. All right. So, that means what? That means that, again, the x plus 1, this x plus 1, you guys, that's still the same. It came from here. Okay. But the this thing right here, the bigger bracket, it's going to become what? It's going to become 2 things. It's going to become that one, and it's going to become this one as well. All right. But that this first bracket came from here. That has nothing to do with this. Okay. This bracket is now this bracket. Okay. Didn't change at all. It just got moved over here. But this bigger bracket now is going to become 2 other brackets as a result of this synthetic division. Let's talk about that. So, as we said, when you do the synthetic division, this thing right here that you did the synthetic division on, that top line right there, that top line will automatically break down to 2 brackets. These are the 2 right here. The first one will always be x right here, x, and then you change the sign of this number out here in order to get what goes with that x. And so that's why we say plus 1 with that. And then the second bracket you get when you try to factor this thing right here, assuming you get a remainder of 0, when you factor this thing right here, that second bracket you get consists of these coefficients, don't they? And then the plus 0 doesn't need to be written there on the end like it otherwise would have in the last section. So we get what? We get 2x squared minus 3x minus 5. All right? And so what do I have now, you guys? I now have a total of 3 brackets being multiplied together with nothing outside of those brackets, just those 3 brackets. And so that means that those are 3 factors. Okay? 2 of them now are linear, aren't they? Because they're degree 1 polynomials. This one, though, is a quadratic factor, isn't it? So, since you have 2 linears and 1 quadratic, it would be natural then to try to take the quadratic one and break it down more. Now, you could do synthetic division on this if you wanted to. We already know that -1 has to work one more time, all right? But because we're used to factoring this type of thing where you have x squared and x and then no x at all with the Berry method, I'll just go ahead and do that. All right, I'll do that. In fact, I'll do that off to the side over here. But you could theoretically do synthetic division as long as you know a factor of this already, and we do, because we know that x plus 1 has to be a factor one more time. And so you know that if you do -1 with this thing in the top line right here, with the quadratic factor in the top line with the -1 out here, you know you're going to get a remainder of 0. And then when you do get a remainder of 0, that means that this will now break down to 2 more factors. Okay, and that's what we're trying to do here. But I'm going to go ahead and do it since we're used to this already. I'm just going to do this in the old-fashioned way here. 2 times -5 is -10. All right. And what 2 factors of -10 are going to add up to -3, you guys? They're going to be -5 and 2. And so we get 2x minus 5. And 2x plus 2, but we have to, what? We have to factor out the GCF out of each one of these brackets to get the final answer there on the Berry method. That has a GCF of 1 right there, so it didn't change. This has a GCF of 2, so when I factor out the 2, I get x plus 1. And so this final quadratic factor right here becomes what? It becomes, and I'll just write down the x plus 1 and the x plus 1 again right there. Those didn't change because they were already linear like we wanted them to be. But then this one right here becomes what? This one right here becomes 2x plus 5 and x plus 1. I'm just taking it right off of here. I'm sorry, I messed up there. I meant to say 2x minus 5. 2x minus 5. Okay, I'm just looking right up here. Okay, I'm just taking that and rewriting it down here. So we have a total of what? We have a total of 4 linear factors, but the important thing is that they are all linear factors. All right, that's what they asked for. Okay, so if this had said multiplicity 2, then you'd have x plus 1, and just a couple of them, all right? But because it's multiplicity 3, we knew that we had to have 3 of those. And so when that type of thing happens, what you can do is you can do -1 on the original function. You can then take the leftover factor after you got the linear factor right here and do -1 again on that. Don't go back to the beginning again, all right? That's not going to do any good. Just take the leftover part, do -1 again. You then get this right here. And then if you wanted to, you can then do -1 on the leftover one here that's not linear. You could do that one more time, and it would have given me the same exact answer that I have here, I promise you. Okay, it would have. So that's what multiplicity means. All right. Okay, number 3 is more of the same here. It's just that we have an imaginary number, but we got kind of used to that whole idea in the last section. All right, so it takes a little bit of work to deal with it, but at least we know what to do. My coefficients here are what? They are 6 for x to the third, 19 minus 6i. That's why that's in parentheses. That entire thing is being multiplied by x squared, and so that entire thing, not just the 6i or minus 6i, but that whole thing is your coefficient. In a similar way, 16 minus 7i, because it's in brackets and it's being multiplied by x to the first, that then is the coefficient of x to the first. And finally, 4 minus 2i is the final coefficient there. It's just there's no x with that, but as you guys know, when you have a polynomial written in descending order, x to the third, x to the second, x, then we have this thing right here that is that has no x at all, and so that whole thing is your coefficient because there's no x to go with it. All right, now let's see what we get here. Drop down the 6. 6 times negative 2 plus I is what? That is negative 12 plus 6i. So I put that here. This is actually going to be easier than that similar type of problem that we had in the last section. Trust me, you'll see why here. The 6i's cancel when I add these together. Remember, when you add together, you guys, a couple of polynomials, not just single terms, or even if they are single terms, all right, when you add together things, you got to combine like terms. All right, well, these are going to cancel when you combine like terms, and so you just get 7 right there, don't you? So then I take 7 and multiply that by this. 7 times negative 2 plus I is going to be what? That's going to be negative 14 plus 7i. And once again, when we add these together, we got to combine like terms, and the I terms cancel again. Okay, so it works out real nice. And then one more time here, negative 2 times this thing on the outside, we distribute again. We get 4 minus 2i. And let's see here. Something went wrong there. Something went wrong there. Let me check that out. So we got oh, that's what it was. Okay, my fault. This is not negative 2 here. It is positive 2, and my eraser's getting really bad now. Okay, so but that is 2. I think we got that sufficiently erased right there. Okay, so that we got that erased, and that's now positive 2. If I distribute positive 2, I now get negative 4 plus 2i. All right? Because, see, here's the thing, you guys. The reason why I knew I made a mistake was because I knew that this had to be equal to 0 down here. They promised me that it would be, because they promised me that this would be a 0, which means that that remainder's got to be 0. All right? And so since it wasn't turning out that way, I knew I had to go fix something. Now all these terms cancel, and so you get a remainder of 0. What does all this mean? Well, this is where we got to be a little bit careful in how we write this. I'm not going to rewrite this big gigantic f of x here. I'll just say f of x is equal to, instead of saying what f of x is, I'll just say f of x is equal to what? What you do when you have a 0 number here that has more than one term in it, you got to use a bracket, right? You got to say x and then minus. Remember, officially, the way you're supposed to write this thing out is you're supposed to say x minus k. All right. It's just that a lot of times when you have a negative k, you change it to plus. But because we have 2 terms here, that's a totally different story. All right, you got to be careful here. So we got to go back to the minus thing, and we got to say minus with the bracket there. Bracket because it's more than one term. If you are subtracting a number that has more than one term in it, you must bracket it. Just like when we multiply something with more than one term in it by something else, you bracket it. When you're subtracting something with more than one term in it, you've got to bracket that as well. Okay, so you got a little bracket stuck inside of the bigger bracket that you would normally have when you do x minus k. all right? Just like with the x plus 1 up here, all right? You got the bracket, but now you're going to need that smaller bracket on the inside. The other bracket's a lot simpler this time. It's just, what is it, 6x squared plus 7x minus 2. 6x squared plus 7x. And I said it again. I meant plus 2, not minus 2, because we did change that to positive 2 right there. Excuse me. All right. So what do we got now, you guys? We've got, and I know this looks kind of weird because of the negative 2 plus I, but this is a linear factor. Remember, negative 2 plus I is a constant number. So it's the only variable is x to the first here. And that's why it's linear. Okay, so the highest exponent of x is x to the first. That makes it linear. This is what? This is quadratic. All right, the little bracket inside of the bigger bracket doesn't count. We're just talking about the two brackets that are being multiplied together that equal the whole thing here. Those two brackets there, not including the smaller bracket on the inside here, those two bigger brackets are being multiplied together. That means that they are factors of this function. Okay, this one is linear, like I just said, all right, because it's just x, not x squared or x to the third. But this one is got the highest exponent as x squared, so that's quadratic. And so again, as we've seen before, all right, if you've got a linear factor and a quadratic factor, or even if you just have a linear factor and some other factor, no matter what it is, keep the linear factor the way it is, all right, and then try to take the quadratic factor and break that thing down to smaller factors until everything is a linear factor. All right, this again looks like the Berry method. Okay, it says here that 6 times 2 is 12. What two pairs of factors of 12 would then add up to 7? Okay, they would be 3 and 4, wouldn't they? 3 and 4, so I'm going to get 6x plus 3 and 6x plus 4. But I got to factor out the GCF out of each one of those brackets there. What happens when I get the 6x plus 3 and I factor out the GCF? I get the GCF is 3, so that would make that bracket 2x plus 1. And when I factor the GCF out of that one, I get what? Well, the GCF there is 2, so I factor that out. I get 3x plus 2. All right. And we now have 3 factors, and all of them are just x, aren't they? No x squares, no x to the thirds. All of them are just x. And so you now have all linear factors like you're supposed to. All right? All linear factors. And so that is how we take a function and break it down to linear factors. All right? Now, what we're about ready to do here on the back side of the worksheet, let me flip that over. Let me try that again there. Okay, there we go. It says here in these next 3 problems, it says for each polynomial function, 1, 0 is given. And they did that in the last problem as well. They started you out with 1, 0, but this time, instead of saying factor it, although that will be a big part of it, it goes one step beyond that. It says find all the other zeros. Here's how you do that. Okay. It says here, if you want to factor it down, and again, when you factor down, you just have to do steps 2 through 5. Okay, but if they want you to find the zeros, then we want to do steps 1 through 6. Okay, and we can kind of skip through most of number 5. We'll get to that. I'll talk about that. But 1 through 6, what does it say here? It says in in step number 1, set the function equal to 0. Okay, you'll see why that's something we would do here. Okay, so I'm going to set that equal to 0. All right. See, remember, you guys, here's why you do it. The reason why you set the function equal to 0 is because zeros are the numbers that make the f of x equal to 0. All right. So if I can solve this equation, that would tell me what x values make the function equal to 0. In other words, make this true. That's what a solution does. It makes this true. It makes it equal to 0. So if I find the solutions to this, I then can declare that those numbers are the zeros. They make the function equal to 0. And so what we're going to be doing here after we set f of x equal to 0 is that we are going to solve this equation using these steps. And what we're going to do in order to solve that is to factor the non-zero side, just like we did when we used the zero factor property back in section 1.4 in order to solve quadratic equations. All right, remember this right here again. You've got a polynomial, and it's not always going to be a quadratic one where x squared is the biggest exponent, but you got something equal to 0 here. You factor it down, you set each factor equal to 0, and then you solve it. That's exactly what we're going to be doing here. There's going to be some slight variations of that as far as what the factors look like sometimes, but that's the idea. You factor it down, you set each factor equal to 0, you solve those resulting equations. It's that same idea. All right, so let's do that here. The problem with this one, though, is that this is the highest degree is 3. And as opposed to that problem I just showed you where the highest degree was 2, which made it a quadratic equation. All right, so we don't do exactly the same method that we did with quadratic equations where the highest degree was 2. We rather have to go through this process that I have listed here on the previous sheet. Okay. Now, what does that say? It says to factor this, and that's why I said factor the GCF in this next step. It's because you always do the GCF first when you factor any polynomial, and I need to factor this thing right here on the left-hand side of the equal sign. So, is there a GCF here, or is it just equal to 1, which is not going to, you don't have to factor it out if it's equal to 1. As it turns out, it is equal to 1, so you can skip the GCF step. If it is equal to anything other than 1, please factor that out. Okay. Take the polynomial factor you still have left over. In other words, you didn't factor out the GCF, so it's still the same thing. And now let's proceed from there. If it's degree 3 or higher, which it is the part that you still have left after you factor out the GCF, or if you don't factor out the GCF, you just look at the whole thing. If it's a degree 3 polynomial, which this is because of the x to the third being the highest exponent, then you follow what it says here. It says use synthetic division to factor it into 2 factors. Since they promise us that 2 minus I is a 0, we can do exactly what we just did in the last 3 problems. We can then plug in the 2 minus I into the outside of the synthetic bar, okay, and we would be promised a remainder of 0, which will allow us to factor this thing. All right, don't pay any attention to the 0 over here. We're just trying to factor the other side of the equal sign. The 0 will come into play at the end when we actually figure out what the zeros are equal to. All right, just looking at the non-zero side of the equation, 1, -7, 17, and -15. All right, what do we get? Drop down the 1. Anytime you multiply 1 by something, it's equal to itself. Okay, adding this together, we get -5 minus I. All right, now here's where it gets a little bit interesting, but we saw this in section 3.2. How do I multiply 2 terms by 2 terms? I put them in brackets. And what do I get here? I get 10, pardon me, -10. I'm sorry, that fell off the screen there. Let me do that again. Put both of these in brackets because they both have more than one term. Multiplying this out, I get -10 plus 5i minus 2i plus I squared, but we know that plus I squared is -1. So negative 10 and negative 1 when I combine like terms is going to be negative 11. That's negative 1. Negative 11 then plus 3i. Okay. Now, bring that right here. Combine like terms right here since you have to add these together. And you get 6 plus 3i. And let's do that whole thing over again here where I now do 6 plus 3i times 2 minus I on the outside. And we end up getting what? We get 12 minus 6i plus 6i minus 3i squared. Remember, minus 3i squared is the same thing as plus 3 because the I squared is equal to negative 1. So when you multiply by the coefficient, it just changes the sign of the coefficient. Plus 3. So we get 12 plus 3 is 15. But then the I terms cancel, don't they? So that whole thing is just 15 with no I anymore. And that's good news because when I add on the final column, we get 0 like we're supposed to. Now, just like I told you guys in the last problem, when you have two terms here in this number on the outside, you've got to bracket that inside of the bigger bracket. So f of x, the original f of x function is equal to what? It's equal to x minus, make sure to use the minus there when you're doing two terms that goes in here, like we did in the last problem, x minus bracket 2 minus I. That's the first factor. That is the linear factor because it just has x to the first. Then the other bracket is going to be what? That's where this part comes in. This right here is x to the second, right here. Okay, and when you have a coefficient, as we saw in the previous problem, when you have a coefficient with two terms, you've got to bracket that. Please do not say minus, okay, say plus, okay, to make sure, and that's just how you got to do it when you got two terms as your coefficient. Say plus and then bracket it. Don't say minus even if the first term is minus. All right, that's just how it's done. And then x to the first, and then put a bracket around this after putting another plus right there, a bracket around this. Okay, so that is a pretty crazy looking factor there, isn't it? Okay, but it's a quadratic factor due to the fact that it is x squared is the highest exponent of x right there. So we again have a linear factor and a quadratic factor over here. Okay. Now, what we can do at this point, normally what I would do is when I end up with linear and quadratic factors, since we aren't required to get everything to look like linear factors, normally when I get down to a linear and a quadratic factor, I will set both of these equal to 0 and then solve those things, and because we know how to solve linear and quadratic equations, which is what they would become. The problem, though, is that when you have imaginary numbers inside of your quadratic factor, you guys, it's okay when it's linear, but when it's a quadratic factor, all right, that's a different story. We can't factor when you've got the i's in here. We can't use the quadratic formula, which is another possibility under normal circumstances. Basically, we can't use that either because of the i's as well. Basically, none of the quadratic methods we saw will normally work when you have imaginary numbers inside of your quadratic factor. So, like I said, normally when you get down to linear and quadratic factors only, you set each factor equal to 0 here. All right. In fact, you know what? I messed up here. I meant to say that this was the f of x is gone now. All right. I meant to say that this was equal to 0. Remember, we set that equal to 0 already. So I just get rid of that f of x and put the 0 there in its place. I just put it on the other side. Still means the same thing. But when I got a linear and quadratic factor, but the quadratic factor has i's in it, what I need you to do is I need you to still break this thing down to linear factors. Okay? In any other case where you don't have i's inside of the quadratic factor, you can just set that equal to 0 if it's one of those problems where they ask for zeros and they don't ask for linear factors all the way through, like we saw in the previous 3 problems. All right. So you do need to actually break this down to linear factors. It seems like it's pretty tough, huh? But I got good news, though. All right, there's this thing called, and it's on the very front side. Okay. At the bottom of the front side of the first sheet there, where they talked about 3.3 at the top, it's called the Conjugate Zeros Theorem. It says if you have an imaginary number that is a 0, and we already know, what was the original 0 here? It was 2 minus I, right? So picture this here. It says that if you have an imaginary number, 2 minus I is an imaginary number, and it's definitely a 0, and we already know it is. They told us it was. Okay, and it's a function that has real coefficients. In other words, no i's in the original function. I'm not talking about the stuff you get after that. I'm talking about the original function. All right, if that has only real coefficients, see how the coefficients of the original function do not have i's in it. Okay, when this happens, and you already know that 2 minus I is a 0, that automatically means that if you change the sign of the second term here, that in this case that would become 2 plus I, that is also a 0. You might be wondering, wait a second though, I thought it said that it's supposed to be minus. Yeah, but if the original one is minus, it goes both ways, all right? If this is minus bi right here, then the one with plus bi would also be a 0. They match up together, okay? So let me just give you another example here. Let's suppose this was a 0. I'm just pretending here. If that was a 0, then this automatically would be a 0 also. Let me do that one more time. Let's say that this was a 0 automatically, and they told us that it was. Okay, then this automatically would be a 0 also. These things always pair up like that as long as the coefficients of the original function are real. That's the reason why, you guys, I did not do that in the last problem. In the last problem that we just did, all right, the coefficients were not real. They had i's in it. So I could not say, oh, hey, negative 2 plus I. That means we can also do negative 2 minus I. No, you can't. Not in that case, because the coefficients were not real. All right? So, because 2 minus I is a 0, that also automatically means that 2 plus I is a 0, 2. Okay? Now here's the thing. This thing right here, this factor right here is a factor that if I were to plug 2 plus I into that, okay, that would not make this factor equal to 0. Okay? And when you have two brackets that equal 0, all right, it is true that either the first one has to equal 0 or the second one does. Okay? So since this number is supposed to make this whole thing equal to 0, because this whole thing is equivalent to the original function, okay, since this thing has to make this whole thing equal to 0, and since it doesn't make this one equal to 0, it then automatically must make this one equal to 0. And what does that mean again, you guys? Since this thing is now a 0 of this, because it can't be a 0 of that factor, it makes this one equal to 0. That means that if I put 2 plus I, let me write it down up here. If I put 2 plus I outside of the synthetic bar, and I put these things in here, 1, I'm just looking at this right here. Remember, as we've done in the previous problems, you now try to break down the leftover factor here, the linear factor. You leave that alone. All right. I need to break this thing down to linear factors, like I said, because you can't set the quadratic factor equal to 0 in this case because of the i's. All right. So because I know that 2 plus I is a 0, and since this number here doesn't make this factor equal to 0, it must make this one. Okay? It has to make one of your factors equal to 0 at least in order to be a 0 of the entire function, which we know it is. So bring down the 1. 1 times 2 plus I is 2 plus I. What is this equal to when I combine like terms right here? It is equal to -3. If I then multiply -3 by this, I got to distribute it through that. Okay, and that's going to be -6 minus 3i, and you can see right there, you guys, when I combine like terms, everything cancels out, and I get 0. What does all this mean? Well, anytime you do synthetic division on something you're trying to factor, and in this case, the thing I was trying to factor was this one right here, the big bracket right here, it breaks it down to what? It breaks it down to 2 more factors, as long as the remainder is 0. That first bracket is going to be what? It's going to be x minus the outside. As always, x minus the outside, and we need to keep it as minus this time because it's got 2 terms on the outside there. And then this right here is what? This right here is going to be x minus 3. I made that bracket way too big, but that's okay. It's better to be too big than too small. X minus 3. Okay, x to the first because this one was x to the second. So x to the first and then minus 3 right there. So these are now all what? These are now all... I was missing a bracket right there, excuse me. All of these are now linear factors, okay, because they all have just x in it. All right, so once you've factored the non-zero side of the equation with 0 on the other side, once you factor that all the way down to linear factors, not that you have to go that far all the time. Like I said, you could do linear and quadratic factors normally and then do this next step I'm about ready to do, all right, with linear and quadratic, but just not in this case, because we can't have a quadratic factor with i's in it, okay? We have to keep going in that case by using the conjugate zeros theorem. But now that I've got all linear factors, you are definitely allowed to what? You're definitely now allowed to set each one of these factors equal to 0. Let's do that. So x minus, I'm just making some room here, so I kind of shifted it over. X minus 2 minus I is equal to 0. X minus bracket 2 plus I is equal to 0. And then x minus 3 is equal to 0. We do the same thing we did, you guys, back when we had the quadratic equations, all right? You get your factors. Once you've factored as far as you're going to go with it, you set each factor equal to 0, even if you've got more than 2 factors, all right? As long as it's the factors, the things that are being multiplied together to equal that entire non-zero side of the equation, as long as it's those things that you're setting equal to 0, that's what's important, okay? So what do we get here? If I distribute out my brackets, I get this. Okay, let's see. And then I still need to get x by itself on these two, so that means I need to add the 2 over and subtract the I over. Add the 2 over and subtract the I over. And so I get x is equal to 2 minus I, x is equal to 2 plus I, and then over here, this one's a easier one. You just have to subtract, or rather add the 3 over. So our final answer right there is these 3 zeros. And I call them zeros because they made the function value equal to 0. Because I set the function value equal to 0 and I solved the equation. All right. So, when they ask you to find all the other zeros after giving you 1 0, you start out with that 1 0, you guys. You do the synthetic division on that. You break it down, and you then go from there. If you've got linear and quadratic, okay, normally you can set those equal to 0, but I had to take this. When you have a quadratic with i's in it, you got to break it down to linear factors. There's no other way to do it, okay, because of those i's. All right. Next one. It tells us that the 1 is a 0, right? So just like in the last problem, all right, and just like what we've been doing all along here, we put the 1 outside the bar, Please notice, you guys, very important. Please notice, there's the one outside the bar right there. But please notice that there is a term missing there, isn't there? Okay. 1, 4. So I got to put the 0 in between the 4 and the negative 5 because the x to the first term is missing. Okay. And now we're ready to do the synthetic division right here. 1. Let me just go ahead and do it here. So, all right. And there we go. Okay, so what does this factor down to now? And which it definitely does because the remainder is 0. F of x is what? It is, oh, and you know what, I stand corrected here. What do I need to do even before I factor it? I need to set this, because they want to know the zeros, we want to set this thing equal to 0. Excuse me for not mentioning that. And then I need to factor this non-zero side, just like I did in the last problem. Okay. So the next step here, which I'll go across here with, we have to factor that non-zero side. The 0 stays the same. All right. And that's going to be what? That's going to be x minus 1, opposite sign of what's up here, x minus 1. And then x squared, I'm just doing these 3 numbers here, x squared plus 5x plus 5. All right, so what we have here now, you guys, is a linear and a quadratic factor. As I promised you, when they're asking for the zeros, they're not asking you, like in the first 3 problems, to break it down to all linear factors. If they just want you to find the zeros, you just need to get down to where you have just linear and quadratic factors, all right? In other words, you can't have like x to the third anymore, but each factor is either linear or quadratic. When that happens, though, you can now set both of these things equal to 0 and then solve those, and that will give you all of the zeros, I promise you, all of them. All right, because as long as you set each factor equal to 0, you're going to have all the answers. All right. Okay, now as you guys know, when you set x minus 1 equal to 0, that gives you x equal to 1 just by moving the 1 over. Now this looks like the Berry method right here, right? To try to solve this, just like we did with this problem here back in chapter 1. It looks just like this right here, doesn't it? But the problem is that this one does not factor. This doesn't factor like that example I just flashed up in front of the screen right there. So as we learned in that same section, when we have a different alternate method that we could use when it's in that type of form right there, and that is what? That is when you can do the quadratic formula. There's other methods we learned as well, but that's usually what you fall back on when you got, you know, the x squared and the x and the constant with the 0 on the other side. You fall back on the quadratic formula. What would that be here if we did the quadratic formula? We would get, and that's back in 1.4 if you want to look at the formula again, but it's negative 5 plus or minus the square root of negative 5 squared. You know what, I'm running out of room here. I'm going to do this off to the side here, and then I'll bring the answer back up here. That'll be a lot easier. So let's write this down here. Negative 5 plus or minus the square root of 5 squared. I'm just following the formula from section 1.4, the quadratic formula. Divided by 2 there, because that's 2 times the first coefficient. All right. What does this end up being equal to? Well, I actually wrote it down back over here. I got the square root of 5, and the reason why that is because that's 25 minus 20 right there. 25 minus 20. All right. And so we end up getting, you can't simplify this any further either. All right, so we end up with x equal to 1 and x equal to negative 5 plus or minus square root of 5 over 2. All right, again, like I said, Once you get down to the linear and quadratic factors, you set them both equal to 0, and you solve the resulting linear and quadratic equation that you get. We know how to solve linear and quadratic equations. That's why it's okay, once you get down to the linear and quadratic factors, to set those equal to 0, as long as the quadratic doesn't have any i's in it, like we saw in this problem up here. All right, because you can't use those normal you can't use those normal quadratic equation methods when you got the i's in there. All right, now, next one here, last one, before we jump to something different. Again, it gives us an I here to start us off. All right. Notice there's a couple of terms here missing. So I put the I on the outside. All right. And we have 1 for x to the 4th, the 0 for x to the 3rd because that's missing, 26 for x to the 2nd, 0 for x to the 1st, and then 25 for the last term there, no x at all. What do we get here when we get that? 1, multiplication, we get I, add, we get I times I is I squared, but I squared is equal to -1, as you guys know. 26 plus -1 is 25. 25 times I is 25I. Anytime you add something to 0, it stays the same, 25I. And then finally, 25I times I is equal to 25I squared. But 25I squared, isn't that the same thing as 25 times -1? Because I squared is -1, which makes it -25. Which then, when we add it together, is going to give me that 0 remainder I want. So, setting this thing equal to 0, okay, like we do here when we are trying to find the zeros, all right, and then factoring the non-zero side, we end up getting what? This thing, when we factor it down, since we put it into the top of the synthetic division here, the first factor is going to be what? It's going to be x, and then since this is just a single term, not one of those problems that has two terms, you just change the sign of that, so now it's minus I. And then the bottom row here, not including the 0 remainder, is going to tell you everything else in the other bracket. So we get x to the 3rd plus I times x squared plus 25x plus 25I with no x at all in that last one. All right. And then so what do we have here? We now have a linear factor, and we have a degree 3 factor, we call it, because the highest exponent is 3. Again, we are not all the way down to the point to where we have a linear and a quadratic. Not yet. Okay, so we got a little bit more work to do before we get to that. Once we get down to that, where you got linears and quadratics, then you can do what we did in the last problem, just set them equal to 0. Here's the thing. Since the original problem, not this part here, this part doesn't need to have real coefficients. It can have i's in it. Okay, since the original polynomial had real coefficients, no i's in it, okay, the coefficients are 1, 26, and 25. There's no i's in there. Since I was a 0, then by virtue of the conjugate zeros theorem that we just talked about, since I is the same thing as 0 plus I, then wouldn't 0 minus I also be a 0? Okay, if 0 plus I, these two things are the same thing right here, and they said that I was a 0 already, we found that out, then that means that 0 minus I is also a 0. But isn't 0 minus I the same thing as negative I? Just like 0 minus 5 is negative 5, 0 minus 8 is negative 8, 0 minus I is negative I. So they're trying to tell us here, let me make a note of this here, that negative I is also a 0. Okay, so since that's also a 0, and since it's not going to make this factor equal to 0, it must make this factor equal to 0. Remember I talked about that earlier, where if you've got two factors and you know that a particular number is 0 and it does not make the first factor equal to 0, it must make the second one equal to 0. And so since it does make it equal to 0, if I put it on the outside of the synthetic bar, okay, I am going to get a 0 remainder when I use that negative I on the outside, and then that's going to allow me to factor that bigger red factor right there when I get a remainder of 0, as I've been doing in this entire worksheet. Remember, this last part here is 25i, okay? Yes, I know I looks like a variable, and we don't put variables in this synthetic division, but remember, I is not a variable. It is a constant number. We just give it a letter, okay? Give it a letter name. The x is the variable here, so the i's have to go in here, all right, as they have on a number of problems we've already done. Let me go ahead and do the normal thing here, all right? Add and multiply all that stuff. And so I end up getting this right here. What is all this? And again, I apologize, you guys. That keeps on falling off the screen there. I need to pay closer attention to that. Excuse me. All right. So doing the normal synthetic division, I get this right here. What does this mean? Again, that first linear factor stays the same, but then the one that we put in the top of the synthetic bar, that breaks down to what two things? The negative I has to change its sign when it goes into this first bracket right here, the first of the two brackets that it breaks down to, not including the one that we're already done with over here. This first bracket is now x plus I, opposite sign of the negative I. And then what does this become here? Well, this is x squared plus 0x plus 25. Okay? And so that is just the same thing as saying x squared plus 25. Like that. All right, so now we now have three factors total there. All right. Since the first two are linear, they just have x, and since the third one is quadratic because it's x squared, I now can set all of those equal to 0. As long as all of the factors are either linear or quadratic, you are now ready to set each one of those equal to 0. Let's do that. Okay, and then let's solve these. The first two are linear equations, so I just move over the i's. I get x equal to I, x equal to negative I. And then this last one here, that's a quadratic equation. Let me show you something here from back in 1.4 again. When you have a situation where you have x squared in your quadratic equation and you have a constant term, actually a couple of them here, 0 and 48, but you don't have the x to the first term here, oftentimes the square root property is best. It means that you get the x squared by itself using the techniques we talked about here, and then you do the double square root thing. Let's try that here on this particular problem. If I move the 25 over in order to get the x squared by itself, I subtract it over, and then I do the double square root. I get x is equal to plus or minus the square root of negative 25. But the square root of negative 25 is what? It is the, as we always have when we have the square root of a negative number. All right, let me just pull that often because I'm kind of short on space here. So let me just do that on a piece of scratch paper here, if I can. You know, let's go do it down here. I can always erase that later. The important thing is that you see how it works now. So this is what, according to what we learned in the past. Actually, we don't even need to write that much. We learned that when you have the square root of a negative number, it's the same thing as I times and then you just change the negative number to a positive, like that. But what is the square root of 25? That is equal to 5. And so the final answer there is 5i. Bringing that back up, we end up with plus or minus 5i. So this last equation here gave us two answers, positive and negative 5i, and then we also have I and negative I over here. So the final answer, final answer, if we just put it all together, is going to be I, negative I, and then plus or minus 5i. You could say plus or minus I on the first two there as well. That's okay if you want to condense that even more. But we have a total of 4 answers there, I, negative I, and then positive and negative 5i. All right, for number 6. So let's review here. When we have when they ask us just to find linear factors for the function, all right, you just need to do steps 2 through 5 right here. Use your steps to get down to linear and quadratic factors. That's what it says here in steps 2 through 4. Get down to linear and quadratic factors right here, and then once you do that, take a look at the quadratic factor, and that is typically, if it's a problem where they want all linear factors, that quadratic factor typically will also break down to linear factors as well, and so you'll be fine. Okay, now when they do ask you to find zeros, though, on the other hand, you need to do steps 1 through 6, although I'll explain here in a second. You can usually skip step 5. All right, but you do the normal thing. You get down to linear and quadratic factors. The difference, though, is that when you get to the quadratic step, all right, you can set the linear and quadratic factors equal to 0 right away. The only time that you can't do that is when if the quadratic factor has imaginary numbers, you can't use the quadratic formula. What you should try to do instead is use the the conjugate zeros theorem. Okay, we saw that in this problem right here where I was stuck, all right, with a quadratic factor with i's in it, and so I used the conjugate zeros theorem in order to break that factor down to a couple of linear factors right here that these became. Okay. But other than that situation, though, once you get down to linear and quadratic factors, you can skip step 5 right here where you try to break down the quadratic factor. You can jump right down to step 6, and like we said, once you get the linear and quadratic factors, you just set them all. You set all the factors equal to 0, and then you solve those. All right, you solve each one. All right, so that is what you do when you're looking for zeros. Again, moving forward here, we're going to see some new stuff here. But I'm going to go ahead and stop the video right here since it's pretty long. So let me know if you have any questions about this so far, and then I'll make a new video for the second half of the 3.3 section. Okay, so take care, and let me know if you have any questions.